Happy Wednesday. Welcome to Off-Campus Learning Day, periods 5 and 6 AP Statistics. This is our lesson. Period 5, I'm going to revisit the colorblind problem with you because we're going to look at it a little more in depth. Period 6 has not seen the colorblind problem, so please take out your Yahtzee notes, and we're going to pick up on problem 6, the colorblind problem. So here we go. We're going period 5. We're going to go more in depth on this. Oh, and by the way, for both periods 5 and 6, the homework that's due on Friday will be paper submission, and it'll be 2 problems that I announce throughout the course of this video. So in order to know what to turn in, and it's going to be different for every person because everyone has a different, you're going to get a different string of numbers when you use your random number generator on your calculator. So I'll be able to tell if you're turning in work that was actually generated during this video or not. So let's begin the colorblind problem. It's page 2 of the Yahtzee notes. So 10% of all males have some color perception defect. And, you know, this time around, let's just, I'll pick 4, if we generate a 4. And if you have something else there, you don't have to erase and correct it, but we're going to do something with the calculator. So make sure your calculators are out and ready to go. So we're going to let 4 represent colorblind. We can pick any one. It could be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And so then we're going to let 0 through 3 and 5 through 9 represent no color perception defect. And no, class is not over yet. We've just begun. So we're going to use the command random integer.
Molly Van Huysen.
And we're back. So random integer, comma 0, comma 9, comma 1. Please type that into your calculator by pressing math probability random integer.
Students, if you are.
Thank you for your patience. So we're typing in random integer 0, comma 9, comma 1. One at a time. And in this simulation, we can say that a component, the first component is pressing enter, so that represents someone walking through the door. A test for color blindness is on the 4 because we decided that 4 is going to be colorblind. So first person is not colorblind. The second trial is not colorblind. Third, the third person is colorblind. So depending on how sophisticated we want to create this simulation, we could say, okay, this first trial has 3 components, kind of like pressing until you get Yahtzee. So we got, according to this, suppose we had our simulation be just 1 trial. So then in this really lame simulation that has only 1 trial, we would say, well, it looks like the probability of being colorblind is 1 colorblind out of 3 people. It's 1/3, not 1/10, like they told us. It's really only 1/3. Well, again, that's kind of lame. It would make a lot more sense to define a trial as having, let's say, 10 components. So we're going to look at 10 people by pressing enter 10 times. In fact, I'll tell you, a much easier way to press enter 10 times is just to press enter 1 time by doing, join me here, press math. We'll go to probability random integer. Let's just pick all 10 people at once. So we've got 0, comma 9, comma, I want 10 numbers. I want 10 people to walk through the door. And I look at them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So according to this first trial, the probability of being colorblind is, how many 4s do I have? I've got 2. I've got 2 out of 10. So the first trial is, in fact, I can have trial number 1 is picking 10 people. What's trial number? Trial number 1, it was the results, or I could say the response on the first trial. Response is 2 out of 10. We're colorblind. So now I'm defining this just a little bit differently. Let me just pause. All right, so the language we're using here is this is the first trial has 10 components, and the result of that first trial is 2 out of 10. Okay, now here's the second trial, and it had 1, 2, it's also 2 out of 10. So the second trial had 2 out of 10 were colorblind. And I press enter 10 more times, you get 10 more components, so I use my calculator to do it like that. Oh, here in the third trial, there were 3 out of 10 were colorblind, so the third trial, 3 out of 10. And I mean, I can decide how many trials. I can say, I'm gonna do 1,000 trials. I'm gonna average out all the percentages. You know, the next one, it was only 1 out of 10. So my fourth trial consisted of 10 components, and only 1 out of those 10 components were colorblind. And I mean, I could stop after 5. Let's say that I'm going to create a simulation in which I do 5 trials. Each trial consists of 10 components, and so in my 5th trial, I got 2 out of 10. So 5th trial, 2 out of 10 were colorblind. So then I average these. The result of my simulation, and if you did it, you would have, you're going to have a different result, because every simulation is probably going to come out a little bit different. But if I average these up and divide by 5, so add them up 2, 4, 5, 6, 7, 8, 9, 10, 10. So it's 2 out of 10. So the result is that according to my simulation, the probability, I can say according to my simulation, 20% of all males have some color perception defect. So according to simulation, 20% of males are colorblind. So that's an example of how to use a simulation to arrive at a probability. And remember, we need to know these probabilities in order to form an accurate map of reality. That's what we're going for in all of this, is we're just trying to get an accurate map of reality, so in case we ever enter a period of darkness, our mental map of reality, our worldview, if you will guide us. So just trying to form accurate beliefs using probabilities. So a second option is to generate random digits from 21 to 30. Just to emphasize the artistic nature of this endeavor, you don't have to go from 0 to 9. You can go from 21 to 30, and let's let 25 represent colorblind. So 21 through 24, 26 through 30 represent no color perception defect. So that means, in fact, let's try this one. Type into your calculator random integer 21, 30, let's take 10 at a time again. Let's do 10 numbers at a time. And on the calculator, 25 will represent colorblind. So I'm going to clear this out. And I'm going to change it. I'm going to go second enter and edit this 21, 30, 10 at a time. I wonder if all those will fit. They don't all fit, but oh, there's colorblind 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So after my first trial, one of the 10 components represented colorblind. So I'm going to say that my first trial gave me a probability of 1 out of 10 is colorblind, 10%. And in my second trial, it's 1 out of 10, that's 10%. In my third trial, I wonder if I have any 25s this time, a 0 out of 10. So 1 out of 10, 1 out of 10, 0 out of 10. Kind of interesting. I'm going to record this. 1, 1, 0. So my second trial, which I'll change colors. Red, green, colorblind is pretty common. So I'm going to change over to green. And this time it's 1 out of 10, 1 out of 10, 0 out of 10, I think is what it was. And, all right, we're back. So we're doing another simulation. This time 25 represents colorblind. So we had 1, 1, I believe that one was 0. The next one is 1, 2, 3 colorblind in the next trial. So we'll make that 3 colorblind. So this simulation might give us a different result. And then I'm going to do one more trial in this simulation, and it looks like there's only one colorblind person in my 5th trial. So here, the second time I did it, let's add up these numbers and divide by 5. I've got 3, 4, 5, 6 divided by 5 is that out of 10. So 6 divided by 5 out of 10 is 1.2 out of 10, so it's 12%. So in my second simulation came out to 12% of males are red, green, colorblind. So notice, in fact, this is going to be a lot like the homework that you have to turn in on Friday, is we're going to do something on the calculator. We're going to simulate 2 things. The first simulation, I'm going to get a different result than you will. You're just going to have to record your simulation. And same thing on the second. So it'll be 2 simulations are due on Friday, and the specifics on those will unfold as this lesson unfolds. All right, number 7. Oh, by the way, this is a problem that 6th period did not do. So, I'm sorry, the 5th period did not do. So 5th and 6th period, we're now together doing brand new stuff that you haven't seen before. Should drink some Pepsi, watered down water every time I say. Instead of using the calculator, sometimes on the AP test, they ask you to use a random digit table. So we're going to practice using a random digit table on this problem. An elementary school teacher with 25 students plans to have each of them make a poster about 2 different states. The teacher first numbers the states in alphabetical order, so 1 is Alabama, and the last one in the alphabet is 50, Wyoming, then uses a random number table to decide which states each kid gets. So we were talking about children, and then all of a sudden we're talking about the offspring of goats. It's kind of weird. This problem does get even weirder though. Here are the random digits. So what we're doing is the teacher says, okay, which 2 states does the first student get? Look at the pairs of digits. Okay, the first pair is, go ahead and mark them off in 2s, in pairs. So the first number generated by this random digit table, if this were an AP problem, everyone would have the same answer. That's why they sometimes do this. Okay, so the first one is 45. And that, by the way, the 45th state, if you were to look at it in an alphabetical list, you'll have to trust me on this, but it's the state of Vermont. Okay, and then the next one is, please select the next 2 numbers, is 92. Since there is no 92nd state, we ignore that one. So since there is no, set is, yeah, I just realized that this should be the word ignored. So the next set is ignored because, or since there is no 92nd state. So the next one, 1 with 0 is 10. By the way, the 10th state for the United States would be Georgia. So here's an example of how a random digit table is being used to say that the first person, in the first student, is assigned Vermont and Georgia. Now, which 2 state numbers go to the second student? So the next 2 numbers would be, you can tell the next would be state number 17, which by the way is Kentucky. And the next one is state number 10, and that's 10 is ignored because it's a repeat. We already handed out Georgia to the first student. It's ignored since Georgia was already assigned or previously assigned. The final state number is 22, which happens to be the state of Michigan. Any questions on problem number 7? If so, maybe you can text it to me. If you don't know my phone number, just guess a number at random. There is a non-zero probability that you will text your question to my phone number. So I can't wait to see if if anyone guesses the correct number. Next, play the lottery. Wheaton Academy is not instructing you to play the lottery. Play the lottery is simply the title of problem 9. Some people play state-run lotteries. State-run lotteries are often viewed as taxes on people who don't know math. So state-run lotteries are there. Some people like to always play their favorite, quote, lucky, unquote, number. Luck, by the way, isn't really, if someone ever says to me, good luck, Mr. Royce, I say, well, luck doesn't exist as a causal entity. Luck isn't something that exists even in the realm of the unseen that actually produces any effects. The God of Israel exists in the realm of the unseen, and he actually does cause effects to occur, but luck doesn't exist in the realm of, it's not doing anything. It's not a causal entity. Assuming that the lottery is truly random, is this strategy better, worse, or the same as choosing different numbers for each play? Now, if the lottery is run by chance or random, it doesn't matter if you play the same favorite lucky number. Luck has to be in quotes to remind you that it doesn't exist as a causal entity. Or if you play different numbers each time, all numbers are equally likely, or rather unlikely, to win. When it comes right down to it, the lottery is a system of taxing you or punishing you. So if you want to be punished, for not knowing very much math, then play the lottery. Bad simulations. Bad simulations. Explain why each of the following simulations fails to model the real situation properly. So suppose you use a random integer from 0 through 9 to represent the number of heads when 9 coins are tossed. Yeah, it's very easy to create a simulation that doesn't match reality. And so that's what we're rehearsing here. So 0 to 9 to represent the number of heads when 9 coins are tossed. So before we take a look at why that's a bad simulation, let's take a look at what a good simulation would be for the number of heads when 9 coins are tossed. If I really wanted to do that the right way, or a correct way, if I want to toss 9 coins and count how many heads, what I would want to do is go to math probability random integer and say that 1 represents heads, 2 represents tails, and I'm going to toss 9 coins, so I want 9 of those. And if 1 is heads and 2 is tails, then it's like, well, the first trial has 9 components, and I've got 1, 2, 3, 4, 5, 6. 6 out of 9 were heads, and then the next trial has 5 out of 9 are heads. The next trial is 1, 2, 3, 4. 4 out of 9 are heads. So this would be a way to simulate the probability of getting any certain number of heads. Like suppose someone wanted to know what's the probability of getting exactly 8 heads in 9 tosses of a coin. You could, instead of pressing enter here 1, 2, 3, 4 times, you could press enter 100 times and keep track of how many of these 100 trials ended up with exactly 8 out of 9 heads. And then that would be actually a pretty clever way to find out what the true probability is of getting exactly 8 heads when you toss a coin 9 times, because it's actually pretty challenging to get the theoretical probability on that. But yeah, you can go ahead and do a technique like this. and it will simulate it for you. So these simulations can help you bypass and get pretty good approximations to some otherwise pretty hard math problems. Why would this be a bad idea? And what is this idea, by the way? This is just using a random integer 0 through 9 to represent the number of heads. I mean, this is way oversimplified. If you think that you're going to calculate the probability of getting exactly 8 heads in 9 tosses of a coin, that would, and if you think that the way to do that is to press math, probability, random integer, 0, 9, 1, and say, well, the probability of getting exactly, or if you want to know how many heads you're going to get when you toss a coin 9 times, you're going to get 4 heads. That's what you should expect, or that's the most common one, or it's going to be 4 heads. That's, wow, that was 3 in a row. Didn't see that coming. So basically, the point is that the outcomes are not equally likely. I mean, the simulation described here is assuming that the outcomes are all equally likely, but it turns out that 0 heads out of 9 does not have the same probability as getting exactly 1 head out of 9 tosses, or 2. And so that's the signal, the fact that these 10 outcomes are not equally likely. That's a signal that this is a bad simulation. For example, the probability of getting, did I say 5 heads? Probability of getting 5 heads in 9 tosses is not the same as the probability of getting 0 heads, but the simulation assumes that they are equally likely. Next, part B. A basketball player takes a foul shot. Look at a random digit and using an odd digit to represent a good shot and an even digit to represent a miss. So, looking at a random digit table, even is missed, odd is not. So that's, I mean, the probability of a randomly selected digit being either even or odd is 50-50. Well, that's assuming, to use this as a simulation, is assuming that a person's free throw percentage is 50%. What if they're only 10%? So, an even odd assignment assumes that a player is equally likely to make it or miss it, assumes that the player is equally likely to score or miss the shot. Equally. Now, in reality, which is a major interest in statistics, we want to learn about reality, the likelihood of making the shot depends on the player's skill, which may be either better than 50% free throw or less than 50%. Let's take a look at part C. Use a random digit from 1 to 13 to represent the denominations of cards in a 5-card poker hand. So suppose a hand has 4 aces. This might be represented by 1, 1, 1, 1, and any other number. The likelihood of the first ace in the hand is not the same as for the second or third or fourth, but with this simulation, the likelihood is the same for each. Yeah. Using random digits 1 to 13 to represent the denominations of the cards in a 5-card poker hand. Yeah, the probabilities of these numbers showing up are equal, 1 to 13, because the probability of getting an ace according to this would be 1 out of 13. The probability that the second one is an ace would be 1 out of 13. 1 out of 13, 1 out of 13. I mean, if you're picking from the digits 1 through 13, the probability of this particular outcome is 1/13 times 1/13 times 1/13 times 1/13. However, in reality, the probability of getting an ace from a 52-card deck in which you have 4 suits, you have 2 black suits, we'll call them for now just black suit number 1, black suit number 2, and 2 red suits, red suit number 1 and red suit number 2. Black suit number 1 has ace, 2, 3, 4, 5, 10, jack, queen, and king. The other black suit, so this is what? Spades and clubs, this is diamonds and hearts. But the second black spade goes all the way to king. Okay, so what's the probability of getting 4 aces in a row? Well, there's only 4 aces in the deck. So the first ace, the probability of the first card is an ace is 4 out of 52. The probability the second card is an ace, well, we've already used one ace, so it'd be 3 out of 51, 2 out of 50, and 1 out of 49. So if you're trying to just pick random digits from 1 to 13 to represent the denominations of the cards in a 5-card hand, yeah, it's possible you could get 4 ones in a row, but the probability of getting 4 ones in a row is, according to this simulation, is that, which is way different than what the probability of getting 4 aces is when you're actually dealing with a deck of 52 cards. So the likelihood of the first ace in the hand, 113, in the simulation, is not the same for the second, third, fourth. So there's a lot of things wrong with this simulation. One of which is that not all 4 of these have the same probability. In reality, I mean, here they are all the same. In reality, they're not going to be all the same. There's a lot of other problems with that simulation. And then wrong conclusion. So a statistics student properly simulated the length of a checkout line in a grocery store, and then the student reports the average length of the line will be 3.2 people. What's wrong with the conclusion? Well, it's arrogant will be. The simulation doesn't tell us the truth about what's going on in the darkness. It just gives us an approximation. The conclusion should indicate that the simulation suggests, non-arrogant, it suggests that the average length of the line would be 3.2 people. Future results may not match. May not match. So what happens in reality or future applications of the simulation may not match the simulated results exactly. But then again, they may match exactly. You just don't know for sure. We're just trying to approximate it. Now, the second part of your notes, and if you're taking notes on paper notes, you already have this. If you don't have paper notes, then you can download it. I've provided those for you. At least I hope I remember to provide those for you. So here are the 2 problems that you're going to have to do to turn in for homework. One is the election problem. We're going to do the election problem here on the video, and then we're going to do it. Then you're going to, since you have a different calculator than mine, or your calculator is going to give you different random numbers than mine does, more than likely. They might match, but it's very unlikely. So you're going to have different results than what we have here. So here we go. You're pretty sure that, I'm just going to pause this. So in problem 15, it says you're pretty sure that your candidate for class president has about 55% of the votes in the entire school. But you're worried that only 7 students will show up to vote. And that's not very many. You're concerned it's only going to be 7 students. So how often will the underdog, that is the one who has 45% support, actually win? I mean, if everyone were to show up to vote, it'd be no problem. We would expect that your candidate would win every time. But if only 7 of them show up, then it's, oh, I wonder which 7 it's going to be. So the answers to this will vary. So I would recommend that you record this information on the notes for off-campus learning day, but then also you're going to turn in a paper submission that has the results that differ, because your random number generator is going to generate different results than my random number generator. But what we're going to have is a component is going to be 1 voter voting. A different mathematical artist might decide that the component is 7 voters voting. But we're going to define, that's why we have to communicate this in writing. The component is going to be 1 voter voting, and an outcome is a vote for our candidate. Okay, so that the outcome is going to be when our candidate wins. So we're going to use 2 random digits. And the 2 random digits will be 00 through 99. We're going to let 01 through 55. So we're going to take 55 of those 102-digit numbers to represent a vote for your candidate. That's your guy. And we're going to let 00, in case that comes up randomly, and also 56 through 99, if those numbers come up randomly, those are going to represent a vote for the underdog. Okay, so this part you don't have to write down on a separate sheet of paper. I'll tell you when you get to the part where you actually have to write for turning in on Friday of this week. So, now that's one way to do it. However, this is from an age before calculators were possible. We could use random integers from 1 to 100 generated by your calculator. In fact, this is what we're going to be doing. We're going to use random integer, more suitable for a calculator age, 1 to 100, comma, 1. And we'll just take 1 through 55 to represent a vote for our guy. And then we're going to let 56 through 100 represent a vote for the underdog. So that's how, an outcome is vote. Now, right now, we're going to have to revisit this phrase, because right now my guess is there's a little bit of confusion in your mind as to what we're talking about with the outcome. So let's just table, if you have that question, which my guess is you do, let's table that question for now. But we have described what a component is. We've assigned meaning to every possible outcome, and outcome is a vote. Yeah, okay. So now let's take some time to communicate to our audience what a trial is. We're going to say that a trial is 7 votes. So a component is 1 vote, a trial is 7 votes. Examine 2-digit random numbers, or it could be some of them are 1, some of them are 2, and some of them are 3 digits, since we're going from 1 to 100. But basically, we're going to examine 7 of the random numbers, and we're going to count how many of the simulated votes are cast for each candidate. Whoever gets the majority of the votes wins the trial. So, we're going to describe the response variable, and this is new vocabulary. A response variable is whether or not the underdog wins or loses. So the response variable for each trial is either win or loss for the underdog. Remember, this is an underdog-focused program because they wanted to know how often will the underdog win. Basically, what percent of the time will the underdog win? Okay, so to calculate the experimental probability, which we have been working with that vocabulary, in order to calculate that, we are going to divide the number of trials divide the number of trials in which the simulated underdog wins by the total number of trials. Okay. Now, it says data from class simulation. If this had been a regular class day, if it had been an on-campus learning day, each student would generate a trial, and the simulation would have however many trials there are people in class. So if there are 20 people in class, there'd be 20 trials in the simulation. Now, this is an off-campus learning day. So I'm just going to ask that you conduct 30 trials. I'm going to conduct 30 trials, and you're going to conduct 30 trials. And then you're going to turn in the data. So this is the part where you should go to a separate sheet of paper, because data from class simulation, since we're not doing a class simulation, we're doing, cross off the word class. Your paper that you turn in on Friday, and we're going to call this problem number 15. Problem number 15 is the first one you have to type in. And you've got to show me what are the 30 trials that you came up with. Now, the 30 trials will be organized on a table where we have trial number, component slash the component outcome. And remember, we use the word outcome as a vote for our candidate. So this is component outcome. So we're going to report the component outcome and then also the trial outcome. What's the outcome of the trial? So for trial number 1, 2, 3, 4, 5. So I'm going to have to do all 30 of them here. And once we get going, I'm going to pause the camera. I'm going to finish it off camera. And I would expect you to pause the camera after we get going, like maybe after the first 3 trials so that you can see how this rolls. I would expect you to pause the camera and complete all 30 trials on your own. And then we'll come back. You'll see my 30 trials. You'll see your 30 trials. And we'll talk about how to wrap up the simulation. So here's how we operate this. We're doing just numbers 1 to 100. Remember, we're saying that outcome is 1 through 55. So on your calculator, you're going to type in random integer. Let me save this. It's going to be random integer 1, 100, 7. Random integer 1, 100, 7. So each trial will be 7 people voting. So let's do that together, and hopefully you've got cleared out. So the first trial will be to select 7 people from 1, 100, 7. Now, we got to figure out how to deal with the repeats. Okay, so as we think about repeats, we have the possibility that some numbers might come up more than once. So instead of 7, let's pick a few extra in case we have repeats. Let's actually pick 9 numbers at a time because we're going to have to ignore repeats. This is common practice in simulation, is to pick a few extras in cases where repeats are not allowed. So on the calculator, we're going to pick 9 people, but we're only going to take the first 7 unique votes. So here we go. 1, 2, 3, 4, 5, 6, 7, 8. If we have any repeats, we can get them. But in the first 7 numbers, I see, and again, my guy is going to be called the, U will be for underdog. So I'm going to just let U represent underdog in my notation. And G is going to represent my guy. Or maybe you think, maybe you're going to think, there's a girl that you're voting for, a guy or a gal. Let's use parallel construction. My gal. So the underdog or my gal. And so what do we have in this first one? In this first one, remember, if it's 1 through 55, it's like, yay, that's my guy. So this first one is, yay, that's my guy. So that's a G. This is my guy. 1G, underdog. 2, my guys. A second vote for my guy. A third vote for my guy. 1, 2, 3, 4, 5, 6, 7. And a fourth vote for my guy. So the first 7, 4 of those first 7 numbers were in the range 1 to 55. And the other 3 were for the underdog. So 4 for my guy, 3 for the underdog. So it was 4G, 3U. 4 votes for my guy, 3 votes for the underdog. So the trial outcome is a loss for my guy. Wait, hold on a second. Find out, we're focusing on How often will the underdog win? Oh, ho, 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 ho. So the is whether or not the underdog wins. So the underdog, wait, 4 for my, so the underdog lost. The underdog lost because you have to get a majority of votes to win. Okay, I'll do one more. My next trial is 9 people, but I'm only taking the first 7 unique results. Is, okay, 1, 2, 3, 4, 5, 6, 7. So I'm just going to go up to here. How many votes for my guy? 1, 2, 3, 4, 5. 5 votes for my guy. Only 2 for the underdog, so that's another loss. So that's 2 of them. I've done 2, hopefully you've done 2. We need to do 30 trials in this simulation. So I'm going to pause the camera. I'm going to finish doing my other 28 trials. You, in the luxury and comfort of your own home or at Wabucks, just down the road at 59 and 64. If you're at Wabucks, you can do this. Just pause the camera, finish your other 28 trials for a total of 30 trials, and then we'll talk about what to do with that. So 28 more trials, ready, go. Okay, I'm not done yet. I want to show you where I'm at so far. I just finished my 8th trial. On my 8th trial, I had 1, 2, 3, 4, 5, 6, 7. Okay, so I had 1, 2, only 2 votes for my guy, 5 for the underdog. So 2 for my guy. Why don't I write that down as 3? Maybe I have 1, 2, oh yeah, it was 3 votes. 12, 10, and 55 are 3 votes for my guy and 4 for the underdog. So that's a win for the underdog. So in my first 8 trials, I've had 1, 2, 3 wins for the underdog. So let's continue. I'm going to pause when I get to 10 trials because that'll be a good approximation. Okay, so I finished 10 trials. And in the first 10 trials, the underdog won 1, 2, 3, 4 times. So that's a rough estimate that the underdog will win 40% of the time. 4 out of 10 is 40%. By the way, there is a way to find out what the theoretical probability is. The theoretical probability is found by doing something that we won't have to do until 2nd semester. This is a more complicated probability, but it's by raising 0.45 times 0.55 to the 7th power and using the binomial theorem to look at that expansion. So this is a preview of something that is in a later unit, but it would be 7 choose 4 times 0.45 to the 4th. Because the underdog has to have at least 4 wins, 0.55 to the 3rd, or the underdog could have 5 wins, 7 choose 5, 0.44 to the 0.45 to the 5th, 0.55 squared, or the underdog could win by getting 6 out of 7 votes, 0.45 to the 6th times 0.55, or by getting all 7 votes, 0.55. Let me change the camera here. So if you were to type that into your calculator, that would be the theoretical probability of the underdog winning when only 7 people show up to vote. 7 randomly selected people show up to vote. So, just so you know, I know what the theoretical probability is. So when you turn in your simulated probability, I'll have a way of knowing how unusual it is to see how it compares to the theoretical probability. But anyway, let's continue on with the simulation. I'm now going to do the data. I'm going to do 20 more trials to get a total of 30. So the next time I unpause, all 30 of my trials will be done. Okay, all 30 trials in my simulation are complete, and it took perseverance to finish this, but I do have evidence that I actually did do all 30 trials in my simulation. And my last one, yeah, I had more for the underdog than I anticipated, but there's a point at which I had 3 wins in a row. Oh my goodness, win. I had 5 wins in a row for my underdog at one point. But let's find out how many there are altogether. What I'm going to do is count how many wins I had out of 30 for the underdog. You'll have to count how many underdog wins you had out of 30. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I had a string of 5 wins there for the underdog. 12, 13, 14. Okay, so I had 14 out of 30 wins for the underdog. Here's how I report this out. 14 out of 30 is what it was last year when I did it. It's different this year. So I say, according to not our simulation, was not a group thing, it's individual. So according to my simulation, I expect, I don't know, but I expect future results may vary. I expect the underdog will win in, and you have to show your calculation here. I got 14 out of 30. So I'm going to say 14 divided by 30 equals, and here's where I go to my calculator, and for my simulation, 14 divided by 30 is 46.6, so I'll say about 47%. I expect the underdog will win 47% of the elections in which only 7 students show up to vote. So that's what you would write at the end of your simulation. You're showing your work. And what you turn in on Friday, there's 2 problems you turn in on Friday. The first problem is number 15, where you show me all 3 columns for all 30 trials, and then a statement where you bring it all together. What it means is that you expect, what's you got? I get 47.5. Is that what I said? I said 47, no, it should be 46.7%. So let's get that fixed. 46.7% of elections. My simulation predicts that probability. By the way, the theoretical probability would be interesting to look at what that is. Now let's go on to our last problem. The last problem of this lesson is a simulation where we're going to try to solve a mystery and come to a verdict about an allegation against varsity football players. So turn to the very last problem, the page 260 dormitory football scandal problem. And again, this is the last one, and then I'll do it with my computer, my calculator. You'll come out to a different result probably with your calculator, and then you'll be able to turn it in. So 2 problems due on Friday. Here we go. 57 students participated in a lottery for a desirable dorm room with a triple. We're in college here, and the dorm room, it's a special one. It has a fireplace, a private bath, and it's in the tower. 20 of the participants were members of the varsity football team. So of the 57 students who want this special dorm room, which I think it has 3 members. So it's 3 people in the room, and 20 of the participants are members of the varsity football team. Well, guess what happened? All 3 winners of the lottery were members of the varsity football team. And the other students cried foul. They said, we believe that someone has cheated. That's their belief. If the probability of all 3 of the winners being varsity football players, given that the null hypothesis is that nobody's cheating, it was fair, so given that there's no scandal, if that probability is too low, then we're going to reject the null hypothesis and we're going to start believing that the football players cheated. So our belief is going to be determined by a probability. So we're going to build a simulation. Some years I've taught 7 steps to building a simulation. We're not getting quite that fancy this year, but you might be wondering, well, what's the difference between a low probability and a very low probability? At this point in the course, we're setting that arbitrarily at 5%. Later on in the course, you will find out how to do it in a more reasonable fashion. So if the probability, and let's go ahead and put the eyeball and the brain phrase up here. We want to simulate the probability of all three winners are VFP, varsity football players. What's the probability? And that's our eyeball phrase. What is the probability that we observe? And that's what we did observe. Here's the pupil, here's the eyelashes, no mascara. What's the probability that we use our eyes and we make the observation that all three winners are varsity football players, given that there is no cheating going on? Null hypothesis is no cheating. So that's the brain phrase. That's what we believe. We're going to give them the benefit of the doubt. We're going to assume that you're not cheating. What's the probability that if you're not cheating, that all three winners are from the varsity football team? If that probability comes out to something less than 5%, like 3%, then we're going to say that's too low. We're going to reject the no cheating hypothesis, and we're going to conclude that the system is corrupt. Something went wrong. So if the probability according to our simulation comes out to be greater than 5%, then we're not going to reject the null hypothesis, and we're going to conclude that no cheating went on. It may be unusual, but sometimes unusual things happen. It's not too unusual. So here we go. A couple of ways we could do this. And just to underscore the fact that you are an artist, it could be that a component is to do the green and the purple version. You don't have to do both of these, but I just want to show you this. It could be a component is one person selected. Selected. Some other mathematical artists might just say that in their simulation, a component is going to be three people are selected. Three unique people are selected. No repeats allowed. No two people are the same. Everyone is unique. You're unique, just like everyone else. A component will be modeled by, and by the way, if you were doing the green simulation, then you could model option 1 by a random digit table. Random digit table. And you could scoop up these random digits 2 at a time. And since we're selecting 57 people, I mean, you could say that we're going to, in the explanation of the process, in the green version, we could say that scooping up digits 2 at a time, if you get anything like 0, 1 through 2, 0, that's going to represent REP. That represents a varsity football player, comma. If you get 21 through 57, in fact, we'll let V represent varsity. That's N, that's going to be a non-varsity player. And then we'd have to say that we ignore. You have to specify what you're going to ignore. We're going to ignore 0, 0. And we're also going to ignore random digits 58 through 99. We should also give directions to start in the upper left of the table. And now, what if we're doing the purple version? So what if 3 people are selected? The purple version is the one that you're going to end up doing for your homework. We're just going to use random integer on the calculator. And we're going to take people from, instead of, we could do from 1 to 57, or we could do 0 to 56 if we wanted to be snarky about it. No, come on, let's just do 1 to 57. But instead of picking 3 at a time, let's pick 5 at a time in case, because repeats are not allowed. And oh, you know what? If we're doing the green version, we'd have to say ignore this. We'd also have to say ignore repeats. Just like we did with the Vermont and the 50 states in the earlier example. But we're going to do the purple version, in which we pick some extra. Even though only 3 people fit in the room, we're going to pick 5 people for the room and take the first 3 that are non-repeating. Okay, so I'm going to continue on with with the purple version, just for the sake of time. We're not gonna end up doing the green one. I mean, okay, you get the idea. There's different ways to do this. But let's just fill in option 2. So a trial is going to consist of as many components as needed to get 3 varsity. Just like we did with Yahtzee, we just keep going until we get a Yahtzee. Here, we're gonna just keep going until we get 3 varsity players. So a trial is going to be as many components as are needed. So instead of screaming out Yahtzee, we're going to scream out 3 varsity to get 3 varsity players in the room. So the response variable, what is the response variable going to be? The response variable is going to be the number of components required to get 3 varsity players. I'm going to give it a letter. Q is going to be the letter. You can pick any letter you want in general, but let's all pick Q for this one. So Q is going to be the number of components required to get 3 varsity players. Okay, so if we were doing a random digit table, we do it down here. So if we were doing option 1, we would use these random digits, which would be kind of fun. But we're gonna do it using our calculator. So 3 columns, trial number, outcome number, and trial outcome. That's for, we're doing y equals, we're doing q equals. Okay. So the way that we're doing this on the calculator is kind of interesting. So we said that a trial, we'll do 10 trials. So the first trial will be, now the component outcome, I'm probably not going to make you write those down. All I want you to write down is how many times did you have to press enter until you got this. You don't have to say Q equals because Q equals is on the top. So I'd like everyone to do 10 trials in their simulation. Let me model my first 2 trials. So what I'm doing is I'm picking by going math, probability, random integer. So 1, 57, I'm picking 5 people. So here's my first trial is going to be to count how many times I press enter until I get the first 3 are in the 1 to 20 range. So now the first component is a fail. So I've got 1, 2, 3 is not okay because not all 3 numbers are in the 1 to 20 range. That's what I'm looking for. Are the first 3 numbers, the first 3 unique numbers in the 1 to 20 range? So count how many times you press enter. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There it is. The first 3 players are all varsity football players. I think that was 17. I could rewind the tape to find out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, that was it, 17. So my first trial has an outcome of 17. Okay, I have to do 10 trials. You have to do 10 trials also. So my second trial third, 4, 5, 6, 7, 8, 9, 10. Okay. So I'm not going to have you copy down what the components were. That would be ridiculous. The point is, it took 17 components to get to not Yahtzee, but varsity. All 3 varsity. Okay, so I'm going to pause the camera. You finish all 10 of your trials. I'm going to do my 10 trials, and then we will regroup. By the way, just an update. I've completed my first 4 trials. I had to press enter 17 times to get all varsity the first time, and then 35. The third one was tough. I had to press enter 70 times before I finally got 3 varsity players in 24. So if some of these you might end up having to go over 100. I just push through those. Perseverance. I'm going to finish my last 6 trials. Okay, so I completed 10 trials. What I found myself doing was just focusing on the second number, and if the second number was okay, then I would check the other ones. So I was checking, is the second number 1 through 20? I probably should have told you this at the beginning, but that helped me stay focused a little bit better, because if that one's okay, then I check the other ones. So, oh, there it is. So that was one, but here were my 7 trials, my 10 trials. What I'm going to do now to get a result for the simulation is to find the average of these 10 numbers. So in the wording on this, I'm going to say, according to the simulation, and what I'm going to do is find, just to see if this makes sense, I want to find the average value of Q in the simulation. So the average value of the number of times it takes, and then I'm going to take the reciprocal of that to get it. So what is the average number of years that it would take to finally get 3 varsity players in the room? This is, I mean, essentially what this is like, it's like it took 17 years, because we do 1 dorm room. We offer this dorm room out once per year. It's like it took 17 years till we got 3 varsity players in there. And then the next time we simulated, it took 35 years until we got 3 varsity players. 70 years. Well, what's the probability that it happens in any one given year? So we want to find the average value of Q. According to the simulation, I'm going to take 17 plus 35. So this is what you would show on the homework that you turn in Friday. Add up your 10 values. 70, 24 plus 3 plus 31 plus ... plus 29 divided by 10. So now I have to take out my calculator and add up these 10 numbers, which I'm going to try to do right here. So 17 is 35 plus, where are the other ones? 24 plus 3 plus 31 plus 13, 10 plus 60 plus 29. Okay, so divided by 10. So it looks like, according to my simulation, it's once every 29.2 years. This happens so according to my simulation, Q is approximately 29.2. And that's 1 divided by Q is approximately, so I'm going to take 1 divided by that number. That's a probability of it happening in any given year. So what is 1 divided by 29.2 is my question. On the calculator, I type in 1 divided by answer is 0.034. Okay, so that's less than 5%. So it's about 0.034. So the probability of 3 varsity players given no cheating is 0.034, which is less than, so we consider it very low, less than 5%. Therefore, I'm going to go to the next page. Therefore, we reject the hypothesis, and we call that the null hypothesis. So let's start using that language now. Therefore, we reject the null hypothesis that there was no cheating. So what's your conclusion? We, using the royal we, really means I, we conclude that cheating occurred to cause the observation. So this is what we believe. We believe that cheating occurred to cause the observation of 3 varsity players. I mean, it does happen sometimes, but it's like, whoa, especially if this were to happen 5 years in a row, we could simulate that also. Of 3 varsity players in the dorm room. I mean, come on, this is unlikely. It only happens 3% of the time. By the way, I would like you to also record a calculation of what the theoretical probability is. The theoretical probability of getting 3 varsity players in the room, see how close it is to 3%. Because there's 20 varsity players out of 57. That's a probability that the first player selected is varsity player times 19 over 56 times 18 over 55. So if we type that into the calculator to get the theoretical probability, I mean, that's the whole point of this simulation, is to simulate this probability, which can be kind of hard to come by if you're not used to doing probability problems. You will be by the end of this course, but let's find out what the theoretical probability actually is. 20 divided by 57 times 19 divided by 56 times 18 divided by 55 is 3.89%. So what did our simulation give? 3.89? We came up with, or I came up with 3.4%. So that just shows the power of simulation to get at answers to probability questions that would otherwise require a lot of experience with probability to get at. So turn in your homework on Friday and have a good night.